Okay, so welcome everybody. Thank you for coming. Well, our speaker today probably needs no introduction, and yet we're having Marco Scarsini today from Louise, and he's going to talk to us about basins of attraction in two-player random potential games. And Marco, the stage is yours.
Thank you so much. I want to thank the organizers for inviting me to this to give this talk in this series. Actually, when I got the invitation, I was too embarrassed to tell them that they had made a mistake. So here I am. So this is a co-author with Andrea, Alfie, and Matteo. This is really family. Andrea used to be my master student many years ago, and Alfie and Matteo were my postdocs a few years back. So let me try to frame it in a way that's suitable for this series. So there are many results in the literature about adaptive dynamics that should lead to a Nash equilibrium in a normal form game. In particular, if you look at dynamics that are called uncoupled, namely where the adjustment of a player strategy depends only on his own payoff function, not on the payoff functions of the other players. It may depend on the moves of the other players, but not on their payoff functions. And in this class of dynamics, Hart and Mascolel proved that there exists no uncoupled dynamics that guarantee convergence to a Nash equilibrium. No matter what, you always find a game for which an uncoupled dynamics doesn't converge to a Nash equilibrium. And the counterexample that they provide in the 2003 paper involve both infinite and finite action spaces. So it's not a matter of what the action spaces are. I mean, there's no convergence. There is always a game for which there's no convergence. More recently, some people started asking the question, is this relevant? I mean, do we care about the fact that in some papers, so in some games, there is no convergence to Nash equilibrium? Translating the question, they ask, how frequently do we find uncoupled dynamics that do not converge to a Nash equilibrium? So they go from a worst case scenario to a typical approach. So, but when you say how frequently, well, this needs a formalization. What do you mean by how frequent? And one formalization was recently provided by a group of people in Oxford. One of them is here. So basically, what they did was to consider classes of games, like ordinal games, that can be counted. So basically, once you fix the number of players and the number of strategies for each player, there's only a finite number of such games when you consider all possible preferences of the players. So once you have a finite number of these games, well, you can count them, and you can see how many of these games satisfy or do not satisfy a certain property. So you can look at the frequency with which a property is or is not satisfied. And in particular, you can look at what happens when you increase either the number of players or the number of strategies. So you look at an asymptotic approach to this problem. In particular, there's a paper by Johnston and et al. In 2025 where they show that if you look at simple uncoupled adaptive dynamics, you get converges to Nash equilibrium almost in almost every large game. So almost every has to be properly defined. It's not the typical almost of probability theory. It's, you know, in the sense of a density over large class of games. But, you know, this is the idea. So basically what they're saying is, well, yes, the worst scenario is such that uncoupled dynamics may not converge, but this is extremely rare, okay? And the approach that they take is an approach which is entirely combinatorial. As I said, you know, they look at finite sets and they count the elements in these finite sets. They count the elements in some subsets of these finite sets. But despite the fact of being entirely combinatorial, there is a strong relation between what they do and the theory of random games. In particular, the way they prove some of the results is through mapping their framework into the framework of random games. So what I want to do in the first part of this talk is to give you an idea of what some of the results in the theory of random games are, and then go from this to the behavior of some adaptive dynamics. So random games have been around for a long time, and basically they answer a question of this type. If we pick a game at random, what do we expect to see? I mean, the question is really not very well formalized. I mean, what do I mean? I pick a game at random. What do I mean? What do I expect to see? So let's try some more precise formalization. Namely, take a normal form game with a fixed set of players and a fixed set of actions for each players. If the payoffs are drawn at random, what do we expect to see? So it's slightly more precise than the question in the top row of the slide, but still, it's not completely precise. Namely, what do we mean if we draw payoffs at random? Okay? And what in the beginning of this literature this was supposed to mean, it was supposed to mean take each payoff to be a random variable and assume that these random variables are IID and I have a continuous distribution. The reason, well, IID seems to be a natural thing. It comes from statistics, from, you know, that's what we do or what we teach students at the beginning, you know, when you sample. And a continuous distribution, the reason for assuming a continuous distribution is to avoid ties in the payoffs. Okay? That's the only reason for that. So this was a standard assumption in this literature. And it, you know, as I said, this literature started in the 60s and it went on. And as I said, this assumption of IID payoff is a natural starting point. Continuous distribution is to avoid ties. Okay? Now, this is the setting. And then the question was, what do we expect to see? And what do we expect to see in most of this initial literature was, you know, do we expect to have pure Nash equilibria in this game? And if yes, how many? Okay, so this is the setting. Now, if you take payoffs to be random, well, pure Nash equilibria may fail to exist. In general, their number is a random variable. A random variable can take any possible integer number, including 0. Okay. So if you want to answer this question, okay, before I go, if you only care about the expectation of the number of Nash equilibria, under this hypothesis that I just told you, it's not difficult to see, it's really not difficult to see, that the expected number of pure Nash equilibria is 1. No matter which distribution you take, provided it's continuous, if the payoffs are IID, no matter how many players you have, no matter how many actions you give to each player, you expect to see one single Nash equilibrium. Now, if you want more than the expectation, if you care about the distribution of the number of pure Nash equilibria, then things start getting hairy. I mean, computing this distribution is absolutely non-trivial. But there are nice asymptotic results. Asymptotic results either in the number of players or in the number of actions for each player. And these results came about around the same time, at the end of the 80s. There was a paper by Aratia, Goldstein, and Gordon in the Annals of Probability in 1989, where they speak about the Chern-Stein method. Chern-Stein method is the method to prove asymptotic results. And they show, as in an example, they show that if you let the number of players in a game diverge and you keep the number of actions fixed, then the number of pure equilibria has a distribution that converges to a Poisson, of course, with parameter 1, because the expectation is 1. And then Powers in 1990, so 1 year later, proved that the same result holds if you let the number of actions diverge and you keep the number of players fixed. So either in the number of actions or in the number of players, the asymptotics lead you to a Poisson distribution of parameter 1. And both these players use Chern-Stein method to prove their results. So one question that is natural to ask is, are the above results robust? Is this Poisson asymptotics a robust result? And in a word, no, it's not. And I'll give you 3 examples that show why it is not robust. So the first one is, what happens if payoffs are not IID? So in a paper that I have with my friend Yasser Rinot in 2000, we proved that if we keep the assumption of independence across the payoffs corresponding to different profiles, but within the same profile, if you allow some dependence, we do it with multinormal distribution, so there's only one parameter, exchangeable multinormal, so there's only one parameter, the correlation coefficient, that counts. Then there is an interesting phase transition, namely, when the correlation is negative, even slightly negative, then the number of pure equilibria goes to 0, both in a number of actions and in a number of players. If the correlation is 0, we have the Poisson. But if the correlation is positive, the number of pure equilibria diverges to plus infinity, both in a number of actions and in the number of players. And there is a central limit theorem. So there is a very sharp phase transition around 0, which shows that, the result that I was telling you about before, the Poisson convergence, is very fragile with respect to correlation in the payoffs. Another example of fragility is due to Berry and Bassil-Tarbush, who proved that if instead of looking at pure Nash equilibria, you look at pure epsilon equilibria, then for any possible epsilon, the probability that a game has at least one pure equilibrium goes to 1. If the Poisson convergence were true, it would go to 1 minus 1 over epsilon, because the probability of having 0 equilibria is 1 over epsilon in the Poisson distribution. Therefore, again, the result is fragile. So if you go from 0 pure to epsilon pure, no matter how small epsilon is, you have this phase transition. And a third situation that shows the fragility is the one where you replace continuous distributions with distributions that have some atoms. So in this paper that I have with my colleagues in Melbourne at Monash, we consider games with 2 actions for each player. So the asymptotics is in the number of players. But we allow for atoms. Okay, atoms imply ties, and ties imply that the number of pure equilibria diverges exponentially, and the parameter alpha, which is the probability of having ties, determines how fast it diverges to plus infinity exponentially. So you see, there is a variety of results that show that we had a lucky, cute result of Poisson convergence, but as soon as you change some small details in the model, nothing holds anymore. Okay, and all these results show interesting phase transitions in some of the parameters of the model. Okay, so far this literature looked mainly at existence of pure equilibria and the number of pure equilibria, the random number of pure equilibria. But even in this paper that you see here, we started looking at something else. Namely, we started looking at the behavior of some dynamics. In particular, we started looking at the behavior of best response dynamics in this class of games. And again, even in the behavior of best response dynamics, there are phase transitions that depend on the parameter alpha, which is the probability of ties. So I'm not going to go into the details of this because it's not relevant for what I want to say. But this was the moving from one focus, the number of pure Nash equilibria, to another one, which is the behavior of some dynamics. Okay. In another paper with 2 of my co-authors here, we consider a class of games that interpolates between games with payoffs that are IID, with the continuous distributions, and potential games. So we have a parameter that governs this interpolation. So if P is closer to 1, you're close to a potential game. If P is closer to 0, you're close to a game with IID payoffs. And again, we look at the number of pure equilibria as a function of P, but we also look at the behavior of best response dynamic to see whether best response dynamic does or does not reach a Nash equilibrium. Now, what I want to do in this talk, so all this was a long introduction. Sorry about that, but I thought I wanted to have everybody on the same page. So what I want to do in this talk is to look at to which equilibrium does one of these dynamics converge. Okay, So in order to avoid issues with existence or non-existence of pure equilibria, we'll put ourselves in a class of games for which pure equilibria exist for sure. So the issue is not whether we converge to a pure equilibrium. Not only they exist for sure, but we know that best response dynamic does converge to one Nash equilibrium. So now the issue really becomes only to which Nash equilibrium does this dynamic converge, okay? So in particular, given that the convergence to one of these equilibria depends only on the starting point of the best response dynamic, we see that we can classify the problem as the problem of basins of attraction. Some points lead, some strategy profiles lead to a Nash equilibrium. Other strategy profiles lead to another Nash equilibrium, and so on and so forth. So we basically want to partition the set of strategy profiles into classes. Each one of these classes maps into one Nash equilibrium that is reached by starting in any point in this class. Okay? I forgot to say it at the beginning. Interrupt me if there is any need of a clarification or if I say something stupid or both. Okay, so let's formalize what I said in words in the previous slide. So the framework that we consider is very similar to the framework of these people in Oxford. Namely, we're looking at ordinal games. So games such that players have preferences over outcomes. And these preferences are strict. So for any two outcomes, each player can say that the first is better than the second, or vice versa. Okay? So we look at two-player games. The reason is really that if we try to do it with more than two players, it becomes really heavily unpleasant from a combinatorial viewpoint. So we started with two players. And we have K strategies, K actions for each player. Okay? So this thing here is the usual definition of Nash equilibrium. So a profile A star, B star is a Nash equilibrium. If player A, the two players are called A and B. Player A prefers action A star to any other possible actions, given that the other player chooses B star, and similarly for B star. As I said, I express everything in terms of these ordinal preferences. I don't need a utility function. If you like to have a utility function, you can always put a utility function on this, but it's really not needed. And that also avoids any temptation to talk about mixed strategies. Mixed strategies are not well defined in such a class of games. Okay. Among this class of games, I will look at the subclass of strictly ordinal potential games. So namely games for which there is a potential function C that represents the preferences of the two players, represents the preference of player A and the preference of player B. Notice that the potential goes the other way around, namely the outcome that is preferred by a player has a smaller potential. Why do we do this? Because we will do asymptotics in K. So it's nice to have the best outcome to be the one with potential 1, with the smallest potential, rather than having to adapt every time I move K. Okay? So this is the setting. So if I have two strictly ordinal potential games that have the same potential, they are statistically equivalent. Namely, they have the same set of Nash equilibria. So once you have a potential game, the Nash equilibria of this game depend only on the potential. Okay? So any strictly ordinal potential game is statistically equivalent to a game where the preferences of the two players are the same. Okay? So given all this, for the equivalent classes of games that are statistically equivalent, we just identify the game with their potential. Namely, if I know the potential, I know everything that's to know about the game. Okay? So each Nash equilibrium of such a game, of such a strictly ordinal potential game, is just a local minimum of their potential. So minimum along the row and along the column. Okay? So among all potential functions that I can choose, I will choose the one that takes value 1, 2, 3, etc., all the way to k squared. There are k squared possible outcomes, so I identify the potential with basically the ranking of these outcomes. Okay, so now the randomness comes in. So I put a uniform distribution over all set of strictly ordinal potential gains with a fixed number of actions k for each player. Okay? Basically, this is tantamount to saying that I pick a random permutation of the integers from 1 to k squared. Okay? So the number of pure Nash equilibria in this game is a random variable that takes value 1, 2, 3, etc., all the way to k squared. Actually, it cannot take values that are too large, because in any row or in any column, there can be at most one Nash equilibrium. Why? Because preferences are strict. So there's only one possible local minimum in each row or in each column. So the maximum number of Nash equilibria in this class of games is actually k. Okay? Because each row or column can contain at most one Nash equilibrium. Okay. That's very well. Now, again, if you look only at the spectrum number of equilibria in this class of games, that's also very easy to compute. And the trick is the same as in the case of regular games. Namely, you look at the probability that the specific profile is a Nash equilibrium. When is this profile a Nash equilibrium? When it's the minimum along the column and the minimum along the row. There are k elements on the column, k elements on the row is 2k, but one element is common, so it's 2k minus 1. So the probability that that profile is a Nash equilibrium is 1 over 2k minus 1. Okay? Now, there are k squared profiles, so the spectrum number is k squared times 1 over 2k minus 1. Okay? So asymptotically, as you let k grow to infinity, so the number of Nash equilibria is about 1/2 times k. So basically, every other row in expectation has a Nash equilibrium, or every other column has a Nash equilibrium in expectation. But what's interesting is that this result is stronger. I mean, actually, there is a stronger result than this. This is not just in expectation, there is concentration. Namely, if you look at the number of Nash equilibria, WK, over K, this concentrates on 1/2. Okay? So this ratio of WK over K converges in probability to 1/2. And that's very useful for what we want to do in the sequel. Is everything okay up to now? Okay, thanks. Now, we'll be looking at best response dynamic, okay? So, what's the idea? I start with the point at time 0. So, I start with the profile A0, B0, okay? And then I let always player A start, okay? And player A looks at all possible other outcomes, keeping B0 fixed, because B0 is the choice of player B. Player A looks at all other possible profiles and moves to the one that's best in the column where B0 is kept fixed. And then we move to player B. And player B looks at the row and looks at the highest, the profile with the smallest potential in that row and chooses that. So at some point, we get to a situation where none of the two players wants to move anymore because they have both reached the minimum in the row and in the column, and that's a Nash equilibrium. Okay? So notice one thing. We chose to have player A always start, and this makes this best response dynamic deterministic, completely deterministic. Okay? Had we decided to toss a coin at the beginning to decide who plays, that would have been the only randomness in the dynamic. Because once you start, even if you say at every time I pick a player at random, given that there are only two players, you must alternate. Okay? So in any case, here, once the game is drawn, the best response dynamic that we look at is totally deterministic. Okay. Okay, this is just the conclusion of the description of the best response dynamic. So, as we said before, the game is a strict ordinal potential. So, a Nash equilibrium is always reached by this best response dynamic. And a best response dynamic never visits a row or a column more than twice. Once because it's visited by the row player, and one because it's visited by the column player. So that means that this, in the worst case scenario, it takes at most 2k steps to reach a Nash equilibrium, okay? But actually, it takes many less, okay? As I said before, once you fix the starting point of this best response dynamic, the whole process is deterministic. Okay. Now, let's define the basin of attraction. Basins of attraction. So, what's the basin of attraction of the equilibrium A star B star? Is all the initial points of the best response dynamic that lead eventually to A star B star. Here I say limit for t to infinity, but as we said before, t doesn't go to infinity because t stops in at most 2k steps. Okay, doesn't matter. So when a point is reached, you can imagine that as time goes by, you stay there. Okay. Now it's easy to see, given that we start with player A. Player A is the one who moves first. It's easy to see that if a profile isn't the basin of attraction of A star, B star, the whole column of this profile is in the same basin of attraction. So when I look at this partition into basin of attractions, are basically partitioning the columns of this potential. So let me give you an example. So here we have this 10 by 10 matrix. This is this random potential. We threw at random 100 values of the potential. And these things in green, these, and these, are the local minima of the potential. Namely, they are the pure equilibrium. And these numbers here indicate the basin of attractions, basins of attraction of those columns. So this column goes to here. Why? I say that we start from here. From here you go to 21, which is the smallest value in the column, and from 21 you go here to 4. Here you start with 56, you go all the way down to 1 and you stay. Okay, etc. So some columns lead to 1. There are 3 columns that lead to 1. Some columns lead to 2. Some columns lead to 4. And 2 columns lead to 5. Okay, 3 is not an Nash equilibrium because it's not a local minimum on the column. Okay. Now, we want to study these basins of attraction. In particular, we want to focus on their size. As before, if you try to do this when K is fixed, goodbye and good luck. It's very complicated. So what we did was to try some asymptotic results when K goes to infinity. So you let the number of possible actions for each player go to infinity and see what happens. Okay. So this is the first result. So let me try to say something about the notation and then explain what we have. So if you take the Nash equilibria of this game, you can order them by their potential. So eta 1 is the equilibrium which has the smallest potential. Eta 2 is the equilibrium which has the second smallest potential. Eta 3 is the equilibrium that has the third smallest potential, and so on and so forth. Okay? So I want to see to which of these equilibria I converge. So how many columns converge to the equilibrium eta 1, to the equilibrium eta 2, etc. When K diverges to plus infinity. So when the number of possible actions for each player goes to plus infinity. So what does the result say? So first of all, notice that when K goes to plus infinity, it basically it's like having a continuum of possible let's say possible equilibrium. Okay. And I look at what happens when I order them, and you notice here that I say for all epsilon between 0 and 1/2. Why between 0 and 1/2? Because of what we said before. The number of Nash equilibria concentrates on K over 2, where K is the number of rows or columns. So above 1/2, there's basically nothing. Cannot hope to see equilibria above 1/2. So this is the index of the equilibrium epsilon K. Okay. So you order them all the way to K, and you have epsilon K. Epsilon K is the number between 0 and K. You take the floor of that. And I look at the size of the basin of attraction of this equilibrium. This size scales with K, okay, because there are K actions, K columns. And I look, and this size is random because I start at random with my best response dynamic, or if you prefer, I pick a game at random, and even if I start always in 1/1, the game is at random. So this size is random. I look at the expected value of that. That depends on epsilon, and this is the result. So this is like a density of a random value. Okay. I'll show you the picture of this density in a couple of slides. Okay?
Sorry, Marco.
Yes,
What can you go back 1 second?
of course.
Epsilon equal to 0 is allowed, right?
Epsilon 0 is allowed, but this is a density.
Mm.
So yeah, epsilon 0 is allowed, the density would be E, but it's a density.
Okay.
Okay.
All right.
You can change it. So now I want to see the ranking of these equilibria. The first, the second, the third. When I say first, second, third, ordered by this potential. So, and I want to see, which equilibrium I reach. Okay. And I can say that, if I look at the ranking of the best equilibrium that I reach. And I want this to be smaller or equal than epsilon k. So I get this distribution function. Okay. So that tells me how these equilibria are distributed according to their ranking. And it's interesting because this distribution function is basically the distribution function of the density that I had before. Okay? And if I compute the expected value of this ranking divided by k, I get that it's about 0.21. Okay, so if you want to see the pictures, so this is the density, small phi that I showed you before, and this is the distribution function. So when we started working at these things, we had no clue what we would get, really no clue. And some of us said, well, we expect to be converging to any of these equilibria with the same probability. So we expect this density to be flat. Okay? And some other like me expected something, something like that. A very high density here and then going down fast. And we were both wrong in the end. So it goes down, but it doesn't go down that fast. Okay, so in the last few minutes, and in the last few minutes of your patients, let me let me say another thing, and then I will go to an idea of the proof. So this theorem says the following. If I look at the potential of the last equilibrium, so I ordered the equilibria from the one with the smallest potential, then the second and the third. So then there is the last one. I look at the potential of this guy. How does it scale? And we see that it goes like k log k. So in probability, this ratio converges to 1. So this really goes like k log k. So it's difficult to expect to see potentials that in equilibrium are very large. Okay. So how does the proof go?
Marco, sorry.
Yes.
Hello. Can I ask a question before you move on to the proof?
Yeah.
Just so the intuition for why the basins of attraction get sort of that essentially if you have a lower potential, you're eating up more, there's more low numbers that you can eat up in your rows and columns in some sense that are not equilibria. Whereas if you go to a is that kind of the idea, or?
Yeah. So, okay. Yes. But okay, let me say, I mean, as I said, I had no intuition for this, and it took me some time to develop some intuition. I'm not sure that I do have it, exact, but first of all, you start at a point, okay? If the point where you start contains, if the column where you start contains an equilibrium, you're there immediately. So, and it may be a very bad equilibrium, namely, it may be an equilibrium with a very high potential, but you reach it immediately. And given that every other column has an equilibrium, more or less, so you get to an equilibrium almost immediately, or actually immediately, with probability 1/2. And for that, you don't distinguish between the first, the second, the third, the last equilibrium. You get them with the same probability. So it's the other half of the probability that makes the difference. And the idea is exactly what you said. The more the potential goes up, the more difficult it is to get there, because you have other numbers that are smaller that you tend to visit more. Okay, but this initial element of equality, because you could get immediately to the column that has an equilibrium, is what makes this curve not very steep. Okay, so there's a combination of the two results. So how do we prove the result? Basically, the result goes by a construction that's based on a coupling. So we suitably couple two processes. So, but to do that, we need a lemma, which is overall easy. So if you take a potential psi and you transform it into a potential psi prime simply by permuting rows and columns, well, nothing changes. You get the same set of equilibria, and the equilibria are just the permutations. The equilibrium under psi prime are just the permutation of the equilibria under psi. Okay, so permutation of rows and columns doesn't change the situation. Moreover, the basin of attractions, the basis of attraction of the Nash equilibria in psi prime are just obtained by permuting the rows and columns of the basis of attractions in psi. Okay, so that's the first result. It's not very difficult to prove, but that's quite relevant. So this is the same matrix that I showed you before, where I suitably permuted the rows and columns. You remember, one was about here. So I permuted row and columns as to put one here. Okay. Then I permuted row and columns as to put two here. 3, I cannot do anything about that because it was in the row of 1. So I cannot do anything about that. Then, I permuted row and columns as to put 4 here, etc. So now I have a matrix that is a permutation of the original matrix. So it has the same equilibria and the same basis of attraction, I mean, permuted. But it doesn't have the same distribution because, I permuted not at random. I permuted according to the values of this potential. But what I will do, the core of the proof, is to construct a coupling of this by throwing values of the potential at random in the matrix, but not all together, one by one, incrementally, in a way that the algorithm that I use produces a matrix which is similar to this, which has the same distribution as this. And that's what we do. Let me just give you an idea. So this is what we call the incremental construction. So that produces a matrix that does not have a uniform distribution, but it has the same distribution as the matrix that I just showed you. And basically, it goes like that. It's quite complicated, but basically, let me try this. So we start by putting 1 here. Okay. And then I use some Bernoulli random variables to decide what to do with the second value of the potential, 2, where to put it. So if certain random variable is Bernoulli random variable is 0, I put it here or here. If this Bernoulli random variable is 1, I put it here. And I keep doing that. So slowly, moving from, northeast down, I fill this matrix. And the way I fill this matrix realizes what I told you before, namely, it has exactly the distribution that I want. So I need some coloring of the matrix as I goes by. There is a, exact description of the algorithm. I don't go through the details because I would lose you completely. And this is how it goes, basically. So you see, now we are at this point, and we move, from northeast to southwest. And this is basically all that I had to say.
Thank you. People, if you have questions, now is a good time.
Thank you for the talk. It was really interesting. Have you thought much about the dynamics where they move at the same time, the players, instead of just taking turns?
Oh, that's
Still in potential games, let's say.
that's very interesting. I think it's a totally different ballgame. I'm not even sure that you get convergence for sure.
I don't
No,
think
you don't.
do.
But you may not.
No, you don't.
You
You
don't.
don't, exactly.
You can cycle back and forth.
Yeah. So, yeah, it's an interesting question, but it brings us to a totally different domain, and Davide knows much more.
Yeah, it's something that we've been thinking about with it over here, and trying to find. We didn't think about doing potential games, but we're trying to find the distribution of over cycles that induces. Yeah, we can talk more another time maybe. Yeah, it's interesting. Okay, thank you.
Yeah, because I mean, the reason here it converges is, at every time you bring the potential down. And,
Yeah.
There's a finite number of possible values that it can take. At some point, it has to stop. But when you have players moving simultaneously, as Davide was suggesting, they both move, and so you may end up to a situation where the potential is actually higher.
Yeah.
And they move again, and they keep cycling.
Yeah.
So
No,
the whole heavy structure of potential game doesn't help you.
Yeah, it's a good point. Thank you.
Hey, Marco?
Yes, Raimundo.
Yes. So looking back at the start of your talk, No, I don't have any specific question, but you said, well, there are some results, and they are not robust. So we look at some other things. Now we have a new result, your result. Is this robust or not? So how robust do you think is your result?
Okay, so to answer your question, I'll get to think of ways to make it non-robust. So
Yeah.
the first thing that comes to my mind would be to replace strict preferences with weak preferences, namely to allow for ties. But that wouldn't change the fact that equilibria exist. Actually, there will be more equilibria. What will change is probably the size of the basins of attraction. That's very true. But I wouldn't say that you'd get something dramatically different from what we got here. Another possibility would be to look at situations where there is even more structure. For instance, not only you have a potential, but the game is symmetric. That wouldn't be so relevant here when you have two players, but when you have many players, one of the things that at some point, I would like to study is the situation of games with a large number of players and the games are symmetric, like, congestion games. And there, I don't know what could happen. Otherwise, I mean, another possibility would be to take not all permutations equally likely. Yeah.
And just to follow the idea a little bit more, so you define these strictly ordinal potential games. Is this the largest class of games where the proof works, or?
Okay. First of all, the class of games was also studied by Basil in his papers, and also Barry has. So you can blame me, but I share the blame with them. They are very nice papers. Yeah, papers. The reason we chose this class of games was what I said before, namely, I wanted to focus on to which equilibrium do you get. I don't want to have to worry about, oh, maybe there is no equilibrium. That's why we chose this class of potential games. But actually, you could have some noise or some interpolation here too between potential and something else. And then you would have that equilibria in any case exist with very high probability. So the case where I have to deal with non-existence of equilibria is negligible, and you can work with that, most likely. But just to give you an idea, I mean, the combinatorics is nasty here already, and it would get nastier. I mean, one thing we try to do at some point, or we hope that somebody else will try to do it for us, is to go from 2 players to more than 2 players. Which in principle, conceptually, is not difficult, but I mean, it's really nasty, even with 3. I mean, But you are a smart boy, Raimundo, you can try.
Thank you. And so, please, if someone else has a question, still it.
Go ahead.
So one more question. Like, I know that you have been looking for random games. What is a good random game? Right? And this is a very particular random game that satisfies some conditions, meaning there exists a pure Nash equilibrium, and moreover, it's reached by player best response dynamic. But so this is for this result. Now, if you have a model of random games and you want to say like how good of a model of a random game it is. This is not the mathematical question of is this the largest class of games that we should be looking at, but how do we know that this class of random games is a good class of random games?
Absolutely. What I would like to do one day, but I'm an old man, so maybe I'll have to resort to somebody else. Would be to say, consider a phenomenon that you can model by some game. In this class, how can I draw a game at random? So that would be, so I gave you the example before of congestion games. What does it mean to draw a congestion game at random? It's still not clear to me. Or even more, I have a class of games, and I know what they model. I mean, I start with an idea of a real problem, and I want to model it with a game in some class. But we know that reality doesn't really always go the way a model represents it. So what if I have a game or a class of games and I add some noise? Take even a congestion games. The congestion games costs go up with congestion. But what if you if you add some noise and they go up with the congestion, but not always. Sometimes they go down a bit. Again, what happens? So, and as you said, these are questions that are not just mathematical, these are more conceptual, and they're not easy to even represent. But we're mathematicians, we try to solve what we can solve, not what we would like to solve. But at some point, I think that going from the classical IID model to models where there is some extra structure, every time requires a new set of tools. And that's why, steps are slow. And there's also the fact that, yes, some people have looked at these games, and but it's not like everybody and his brother jumped on the train and started random games. It's still niche. Maybe one day somebody will come with some very nice idea, and it will become less niche. I mean, I think that what Bessel and his co-authors are doing, in this purely combinatorial framework is very nice and could be the way to go.
So keeping it very high level and getting away from this purely combinatorial world, do you think those techniques might somehow apply to basins in mixed games, or that's a completely different beast?
Mixed games have been studied by some people, some very good people. I'm trying to remember the names, but they will come. Barani has a paper, Andy McNeil has a paper. So there are some results. They are, as you said, totally different beasts. The tools that are used are completely different. That's why I usually don't mention them when I give these talks, because it's a totally different way of looking at the problem, and even the basics are different. I mean, in all that we have here, in the whole literature, if you have, look at the IID case, if you have a continuous distribution, any other continuous distribution gives you exactly the same result. There, the fatness of the tails of the distribution have a very strong role in the results. So it's really something else. And I'm not saying it's not interesting, it's very interesting, but it's something different.
Any more questions? Okay, so let's thank Marco again.
Thank you.
I'm going to stop the